Hey junior scientists! Ever wondered from where do we get fresh water for our daily needs? One of the main sources for fresh water is surface water such as lakes and rivers. But these water sources are getting polluted more and more day by day. And one of the main polluters of these resources are industries that dump sewage water into these water bodies. This was the reason chemical oxygen demand aka COD was formulated. Let's learn more about it. Meanwhile, I will show you how to perform it in lab using open reflux method. In environmental chemistry, chemical oxygen demand acts as the detective of water. It tells us how polluted a water sample is by measuring how much oxygen is present in that water sample. What I mean by this is when we have polluted water like from factories, it often contains substances that can harm the environment. And when these industries dump that polluted water into water bodies like lakes and rivers, those pollutants in the sewage water eats up oxygen from the natural water bodies, which is dangerous for aquatic life, as they need oxygen for their survival. Hence, COD test is conducted on waste water of industries before dumping it back. There is a reason we call it oxygen demand. COD test works by adding a strong oxidizing agent to the wastewater, which makes the pollutants react and use up oxygen dissolved in that wastewater. The more polluted the water is, the more oxygen it consumes, and the oxygen demand afterward the test is calculated. We express COD in milligrams of oxygen per liter of the solution, which is equivalent to parts per million, which in simple terms is 1 part of the solute, that is oxygen, per million part of the solution. Many governments impose strict regulations regarding the maximum limit of chemical oxygen demand allowed in wastewater before it can be returned to the environment, and if it crosses a certain limit, a warning is given to that industry. For example, as per General Standards for Discharge of Environmental Pollutants published by Kendriya Pradushan Niyantran Board in India, the maximum allowed COD for India is 250 mg per liter. I will provide this PDF for reference in the description. In the late 1800s, as industrialization progressed, concerns about water pollution began to grow. The discharge of industrial wastes into water bodies raised questions about its impact on aquatic ecosystems and public health. In the early 20th century, the focus shifted to understanding the oxygen demand of organic matter in water, and from there the concept of biological oxygen demand, that is BOD, emerged. We will learn about it in the upcoming video. COD was developed in 1920s as an alternative to BOD because it is more industrially applicable. So, now we know why we bother so much about COD. Now let's learn what are the methods to measure COD. From its invention, COD has developed drastically as per modern technologies and availability of resources. In university labs, however, classical methods are primarily utilized to understand the basic principle. There are several methods to measure COD, one of which is called the reflux method. It is of two types: open reflux method and closed reflux method. In closed reflux method, also called as Hatch method, the reaction takes place in a special type of sealed container known as COD digestion vial or cultural tube, and the sample required is very small in volume. The vials are placed in a COD reactor or a COD digestion block. They allow precise temperature control during the reaction. But our focus today is classical open reflux method. The chemicals we need to perform COD by open reflux method are 1:4 dilute sulfuric acid. Potassium iodide crystals. Starch solubles to prepare starch indicator, sodium thiosulfate solution of concentration N/80 that is 0.125 normality. Potassium permanganate solution that too of 0.125 normality. I will start by boiling water to prepare starch indicator, as we need boiling water for its preparation. If you know how to prepare it, you can skip this part. To prepare it, I am taking a 100 milliliters of distilled water in a beaker and keeping it to boil on my heating plate. Do you know why we need to prepare starch freshly every time? The reason behind it is starch indicator tends to degrade over time due to external factors such as exposure to air, light, and microbial contamination, and using an aged starch may not produce a clear and distinct color change during titration. Now, as water is boiling, I will prepare the chemicals of concentrations I need. As I don't have the perfect concentrations, you can skip this part also if you have the chemicals. To prepare the solution, we need 2 standard measuring flasks of 100 milliliters and distilled water that I am taking in a beaker. I have 0.4 normal sodium thiosulfate solution and 0.1 normal potassium permanganate solution. But I need 0.0125 normal solution of both. So, I need to dilute the solution with distilled water. The amount of reagent that has to be diluted can be calculated by using equation of dilution. So, as per this formula, I need 12.5 milliliters of potassium permanganate and 50 milliliters of sodium thiosulfate solution and dilute them both to the mark on the respective standard flasks to get 100 milliliters of solutions of correct concentrations. After washing the standard measuring flasks, I am taking my chemicals in a beaker for easy handling. I am starting by making sodium thiosulfate solution. For that I am measuring 50 milliliters of 0.4 normality sodium thiosulfate solution and transferring it to one of the clean standard flask. I am using measuring cylinder for ease of handling. You can use a pipette if you want, but avoid any spills as this will change the concentration of the solution. Now, to prepare potassium permanganate solution, I am measuring 12.5 milliliters of it and transferring it to another standard flask and diluting it till the mark, keeping in mind the upper meniscus. Meniscus is the upper curved surface of any liquid that is formed when it is in contact with a solid surface. I am labeling the flasks to avoid any confusion between the reagents during the experiment. Our chemicals are ready. I am keeping everything aside for a while and cleaning my space for the real work. The water we kept for boiling must be ready. Now, it's the time to add starch solubles to it to prepare starch indicator. To do that, get to your electric weighing balance. Switch it on and wait for it to stop fluctuating. In our academia, we usually weigh by keeping a filter paper on watch glass, as some solids tend to stick to watch glass. If you have more sophisticated methods to weigh chemicals, you are good to go. I only have this as my option. As I have boiled a 100 milliliters of water, I am taking 1 gram of starch. The electric balance I have fluctuates a lot and this creates inaccuracies. See? To avoid it, make sure you have modern and sophisticated devices. But as a student it is alright. Now I am carefully removing beaker from hot plate using tongs and adding my starch solubles. I am stirring it continuously using a glass rod to dissolve starch completely and obtain a clear mixture. Water is boiled to prepare starch to ensure complete gelatinization. It is a process in which starch granules absorb water, swell and eventually burst, releasing starch molecules into the surrounding liquid. Gelatinization helps with its stability. After everything has dissolved, we will be left with a clear solution of starch indicator. I am keeping it back on the heating plate for further boiling, but this time I will turn off the heat as the heating plate will be hot for another 30 to 40 minutes. Now we are ready to do the real work. We need to collect our effluent samples and titrate it against sodium thiosulfate solution. Effluent samples are basically samples of wastewater. For titration, we need typical classical apparatus used for titration. These are a burette, a pipette with a pipette bulb, two stoppered bottles. Some common measuring apparatus such as measuring cylinders and droppers. And distilled water and beakers. Now wash the apparatus thoroughly. Make sure to give apparatus a chemical wash after washing with distilled water to ensure more accuracy. I am keeping everything aside and getting my effluent samples. The samples while performing COD are taken in a stoppered bottle to avoid contact with oxygen in the air, as this might affect the oxygen concentration in the samples. Firstly, I will wash my stoppered bottles with distilled water. I am taking 10 milliliters of distilled water as a blank and 10 milliliters of tap water as my effluent sample, as I don't have access to any industry, and it will be fun to know how polluted our university's tap water is. You can use any sewage water, and I encourage you to open your horizon to different types of effluent samples. After carefully transferring my samples in their respective bottles, I always label them to avoid confusion. Our blank and sample are ready. Now I am adding 5 milliliters of dilute sulfuric acid to both of my stoppered bottles to create acidic conditions. Now, I am adding 10 milliliters of potassium permanganate to each of the bottles. After adding it, what will happen here is potassium permanganate will react with organic compounds in the water and oxidize them to carbon dioxide, while sulfuric acid will provide the necessary acidic condition. The overall reaction can be given as: do you know that for certain samples, such as those containing chloride ions, we add a small volume of mercuric sulfate, but not in our case? After adding potassium permanganate, we are supposed to mix the contents with gentle rotations, as doing it vigorously will change the oxygen content in it. Let's get to our water bath, turn it on and set the temperature to 70 degrees Celsius and give our samples a sauna for 15 minutes. The reason behind heating is it helps in complete oxidation. And the samples are heated indirectly using water bath instead of heating plate or burner is because it ensures even heating and is preferred when we need to heat a flammable sample. In between the time our samples are heating, I will do some other stuffs like washing and filling the burette with sodium thiosulfate. As you can see, our samples are perfectly hot, and you may notice that the level of volume of our effluent sample is reduced quite a little as compared to blank, even when the stoppered bottles were closed. The reason behind this could be presence of volatile substances in the tap water. After setting my burette, I will remove blank and sample from heat and let them cool down a bit. Our samples are cooled down now. I am adding 1 gram of solid potassium iodide in both of the bottles. After which we need to incubate the samples in dark for 10 minutes. At this stage, the excess potassium permanganate reacts with potassium iodide in acidic conditions, resulting in the formation of molecular iodine in the process. The equation for this reaction can be given as that brown color is nothing but the color of free iodine. Close the bottles and incubate for 10 minutes. The reason behind incubating is the risk of light-initiated unwanted chemical reactions is reduced. Now it's the time for titration. Let's get our samples. Look at that characteristic brown color of iodine. We will add 2 to 3 drops of our starch indicator that we prepared before in both of the bottles. After adding the starch, the solution will turn dark bluish. This is because the starch is interacting with the excess of iodine to form a complex. That complex is bluish in color. This complex is reversible, and after addition of sodium thiosulfate, iodine will be reduced to sodium iodide, and hence there will be no iodine left to form the complex. And hence starch comes back to its original colorless form, indicating that endpoint is reached. Let us compare the endpoints of both blank and sample and see which has more pollutants. As I said before, the endpoint is achieved when the sample turns colorless. So, an indirect relation can be understood that the more polluted a sample is, the more oxygen is consumed during oxidation, and hence, the lesser the oxidizing agent is left. The lesser the oxidizing agent left, the lesser the potassium iodide is needed and the lesser iodine is formed. And hence amount of starch complex is formed is also small. That is the reason endpoint is reached earlier in more polluted sample. So, we can say the amount of dissolved oxygen in tap water is less. Also, usually the sample is mixed using a magnetic stirrer, but I don't have it. So I need to constantly shake the bottle during titration. See, the end point is reached earlier in effluent sample. Take as many concordant reading as you need to ensure accuracy. Now, we are done with our experiment. Be a good student and follow all the lab protocols. Clean up everything before you leave. And happy experimenting!